Here are the notes for some physics problems from Chapter 13. Numbers 24, 25, 29, 33, and 40. The topics we'll be talking about here specifically are escape speed, what that means, and also gravitation inside of the Earth. So we took some notes on that, just to remind you for the first few problems when we're talking about gravitation inside the Earth, these first two, or inside a spherical shell. You only, so if there's, let's say we have a sphere like this, and you are at some distance here, then the only part of the sphere that you feel gravity from is the part of the sphere that is at or inside your radius. Right? And I'll also remind you, I'll remind you of number 25, because that's where we need it. All right, so number 24, you got a diagram in your book, and they want to know what are the magnitude of the net gravitational force on a particle of mass m due to the shells and the particles located at a radial distance of a. So for 24 part A, I have a particle that's outside of both of the spheres. So that means it's going to feel the gravitational attraction from both of them. So it's going to, the gravitational force on it will be the force from both of them added together. So that's G m2m over r, and the distance is a, right? Because we're talking about distance to centers, so maybe the other thing we note is that it doesn't really matter how your sphere is distributed as long as it's uniform, as long as the center of mass is still the center. So if I have a thin spherical shell that has exactly the same gravitational attraction on something as if all the mass was concentrated at the center, or all the mass were totally uniformly distributed throughout, or any variation of those things. So it's as if all of the mass were just at the center. So for this first one, A, that's my outer shell, plus the inner shell, I have G m1 m over the distance, which is also a squared. Right? So you could combine those terms if you want, or just leave it like that. They have a common denominator, and you could factor some stuff out. Maybe it's helpful to see that it's in fact just this. So I think that maybe the most confusing thing about this is that this A, this R number that you're plugging in here, it's the distance from the point to the center of the object, right? And both of these spherical objects have center in the very center of the diagram. So this is not a radius value, it's the distance between the centers. Got to remember that. So for part B, particle B is in between the two shells. So that means it feels no effect from the outside shell, M2. It only feels gravitational force attraction to the inner shell. So that's a G m1 m over, and that's at a distance of B. So it's only that one. And part C, it's inside both, so there's none. Now there's still gravity, right? I mean, it's still attracted to all those. It's just that all of the bits of gravity cancel out, right, from all of the parts of the sphere that are all around it. And it doesn't matter where you are inside that shell. That's true. It's a hard calculus problem to demonstrate that that is in fact true, not one that we're going to look at. But it is true. All right, number 25. Solid uniform sphere has a mass of 1 × 10⁴ kilograms before, and a radius of 1 meter. We want to know what's the magnitude of the gravitational force due to the sphere on a particle of mass m located at a distance of 1.5 meters from the center of the sphere. Well, if it has a radius of 1, then for part A, I'm outside the sphere, right? Here's the radius of 1, and 1.5 would be here, so I'm at a point outside, so I feel the whole gravitational, the whole deal. So that would be, let's see, gravitational force would be G M M over R squared. And I suppose we could simplify that some. So what does that come out to be? About 3 times 10 to the negative 7th. And then that's still variable m. Part B. Now we are inside of the sphere. If its radius is here, so we're only here at a distance 0.5, which means we only feel the gravitational force from this part of the sphere. And remember, since this is a three-dimensional object, the mass of a core of the sphere, we'll call that m core, at radius r is equal to r cubed over r cubed times the mass of the whole thing. Right, so it's some fraction. So if you're halfway in, like we are here, that's 1/2 cubed over the whole thing. It's 1/8, right? And it's because this is a linear measurement, and I think you probably remember from geometry class that when you blow things up or shrink them down by a scale factor, if they're two-dimensional, you have to square the scale factor, and if they're three-dimensional, you have to cube the scale factor. So that's what's happening here. So that means my mass here, I have 0.5 cubed over 1 cubed times the whole mass. That's 1/8 of the mass. So let's see, what's that over 8.1251.25 times 10 to the third, I think, kilograms. I should not do that without a calculator. I don't know where my calculator is. Might have to go get it. So that's the mass now of this core. So my gravitational force is G M oops, that's 10 to the third m over r squared. And I am going to run and get my calculator. Don't go away. Got it. I'm coming. So we'll just make sure that we did this right. G times m, and then that's just the variable m, so I'll leave that there, divided by r squared. It gives me, oh, I don't like that. Is my g still g? Nope. Something happened to my g. Let's try storing g again. So g is 6.67, whoa, 6.673 times 10 to the negative 11th. Store that in as g. Alright, and then there it is. There we go. That's better. So that's 3.34 or so times 10 to the negative 7th times m. Right? So it's maybe interesting just to compare those numbers. We're much closer in here, so there's less of the sphere that's causing the gravitational attraction. But because we're closer, that ended up making a bigger difference. When we were out here at 1.5, we actually have a little bit more gravitational force here than we did when we were out here. So that's just interesting to think about. And C, trying to generalize this result, what if you are at some distance r from the center of the sphere? Well, at some distance r inside the sphere, then the mass of the core, we kind of set ourselves up for this here, didn't we, is r cubed over r cubed, where this is the whole thing, so that's like 1, right? And that's the where I am, that r cubed, times the whole mass. So if I plug this in, this is my m, right? That's the mass of the core. So my gravitational, my big G gravitational force is G times this mass, r cubed over r cubed times m times our little m over r squared. And important to note here that this is, I'm at a distance r from the center, so the r here, the distance between the centers, is this small r, not the big R. The big R is the fixed radius of this. That's a constant. And simplifying that, you can see that a couple of the little r's cancel out, and you get G m over r cubed, so that r cubed, and then two of these cancel, times r. So this is the only variable here. So that's interesting. It's actually linear. So when you are at the very center, if you were going to plot what's the gravitational force when you're inside the radius of this thing, when you are at the radius r, you get gmm over r squared, right, when you're right at the surface. And then as you move inside, it goes linearly, right? It's just directly proportional to, that's your constant of proportionality. And then when you get outside of it, then the r squared kicks in, and you get something that looks like this. But when you're inside it, it just tapers off like a linear function, like that. So that's interesting, for sure. Number 29. We have a potential energy function, which you have in your book to look at, and it gives the potential energy of a projectile plotted outward from the surface of a planet of radius rs. What least kinetic energy is required of a projectile launched at the surface if the projectile is to escape the planet? So I'll just sketch down the important details of the graph. So here's the radius there, and this is looking like so, something like that, with a scale -1, 2, 3, 4, and sorry, that's supposed to be 5 there, right? So this is the potential energy function of the projectile, right? So what I'm going to notice here is that at the surface, the potential energy is -5 times 10 to the 9th joules, right? That is an important point on that graph right there. So if I make my energy diagrams here, at the surface of the Earth, I know that it has some gravitational potential energy. I know how much. I just looked at that right here because this is right at the surface, plus the kinetic energy that it would need to escape. And then here, when it escapes, we say that escaping means it's escaped right off the page there, at r equals infinity, and that we define that to mean that is when the potential energy is 0. And it just barely makes it to there, so the kinetic energy is also 0. That's our definition of escaping. It makes it to infinity just barely, right? So it has a kinetic energy of 0 and a potential energy of 0. So if you want to escape from here, that's just kidding, that's not a word, it's escape, then you want this total energy to be equal to this total energy. So 0 must equal ug at the surface plus the kinetic energy required to escape. So, and what do they want, the velocity? Well, at least, oh, they just want the least kinetic energy, so I'm just solving for this. So that would be 0 is equal to negative 5 times 10 to the 9th plus the kinetic energy required to escape. Well, there it is, right? So the kinetic energy required to escape has to be equal to 5 times 10 to the 9th joules. That's it. So not hard math-wise, just maybe some thinking about what we were given and what to make of that graph. Number 33. What multiple of the energy needed to escape from the Earth gives the energy needed to escape from the Moon and from Jupiter? So the energy needed to escape from the Earth, well, that's this deal again. The energy needed to escape from the Earth is, I'm just going to borrow from my diagram here, it's the UG plus the escape energy, right? And that totals up to 0, right? So when we say what multiple of the energy needed to escape, we're considering here, well, let me draw, so from the Earth. This is the radius of the Earth. Then here at escape, just like in our last problem, the total energy, oh my goodness, did I do a small g there? Look at that. Sorry about that. It's embarrassing. UG would have to be 0, and K would have to be 0. Which means down here that UG plus K would be equal to 0, right? And that's always negative, so this is some positive number. So the kinetic energy required to escape is always G M M over R, right? This is negative G M M over R, so I move that over here. So that's how much kinetic energy is required to escape. So we just need to compare that for these different planets. So the escape energy for the Earth is equal to G mass of the Earth, which is 5.98 times 10 to the 24th over the radius of the Earth, 6.38 times, or 37, whatever, I don't know, remember what they give in our book, one of those, times the mass, whatever mass we're launching up there. That's going to be the same in all these, so when we just compare multiples, that's going to cancel out. The kinetic energy required to escape from the Moon is G times, I don't know these off the top of my head, and then, so mass of the Moon over radius of the Moon, and then Jupiter, I definitely don't know those. So let me look those up in the back of the book, in Appendix C, some astronomical data. Let's see. We have, where's the Moon? Oh, there's the Moon. So the Moon has a mass of 7.36 times 10 to the 22, and it has a radius of 1.74 times 10 to the 6. And Jupiter, let's see, mass is 318 times the mass of the Earth. That's annoying that they give it like that. Maybe not. Maybe it's better. I don't know. 318 times the mass of the Earth, which is 5.98 times 10 to the 24th. So that's 1.90 times 10 to the 27th. And the radius, the equatorial diameter. Well, I guess. So the diameter, so the radius would be half that. So they give that as 143,000. So it's 143,000 divided by 2. That'd be the radius. And this is in, oh, wait a minute, diameter, kilometers, yeah. So that's actually, this is in kilometers, so that times 1,000, and let's do that in scientific notation, and have my calculator do that for me. So 7.15 times 10 to the 10th. Right, that's because I hit enter twice. Multiplied by 1,000 again. Didn't mean for it to do that. Okay, so now we just need to figure out what these numbers are and compare them. So here, since we're only doing ratios, I'm going to do them all as with a GM in there and just compare these numbers. So they're all multiples of GM. I don't need to multiply that G in there since they all share that in common. I just need to do the, so you see what it boils down to, the escape. It's just the ratio of the mass to the radius. So 5.98 times 10 to the 24th over 6.38. They give 6.37 in our book. I'll do that, sorry. I've seen 6.38 in other places. Depends on where you are. E6, so that's 9.39 times 10 to the 17. All right, for the moon, 7.36 times 10 to the 22 divided by 1.74 times 10 to the 6. That's 4.23 times 10 to the 16. And Jupiter, 1.90 times 10 to the 27 divided by 7.15 times 10 to the 10. 2.66 times 10 to the 16. All right, how did we do there? So, something I don't like here. I don't think I like our answers here. Oh my goodness, you know why? Geez. No, I take that back. So I'm looking at the answers in the book, and they're not in any kind of agreement with what we have here. And I'm trying to reconcile that with this. And I really don't want to. I'm 25 minutes into this video. I don't want to scrap it. So let's see. What are we doing wrong here? The escape energy. Hold on. I'm going to keep talking. Hope that we can figure this out so we don't have to give up the I guess I could possibly have misinterpreted. I don't think I did. The what the escape energy is. Well, I guess I'm going to go on and try to figure out later, I suppose, why this didn't work. Did we misinterpret what they were asking us for? Jeez, I don't feel like we did anything wrong there. This was number 33, right? So 33. What multiple of the energy needed to escape from Earth gives the energy needed to escape from the Moon and from Jupiter? In all those cases, to make it to escape, that's infinite separation, and the kinetic energy is 0. So that means the total of these two has to be 0, which means that the K must equal GMM over R. Well, I'm not sure what to tell you. I like our answers here. I know that the escape velocities are going to vary more significantly. Well, okay. So anyway, if you think you know what I did wrong there, or maybe we didn't do anything wrong and the book is wrong, but I'm going to stick with this. And if I realize what I did wrong, I will address it in the comments. Okay? Sorry for any confusion there. So last one, number 40. We have a projectile shot directly away from the Earth's surface, neglecting the rotation of the Earth. Neglect the rotation of the Earth. What multiple of Earth's radius RE gives the radial distance a projectile reaches if its initial speed is half the escape speed from the Earth and its initial escape energy is half the kinetic energy required to escape the Earth? And then what's the least initial mechanical energy required at launch if the projectile is to escape the Earth? I think we know what that is. It's 0, right? So the answer to part C is 0. So part A. What multiple of Earth's radius gives the radial distance a projectile reaches if its initial speed is half the escape speed from the Earth? So remember from your notes, it's easy to derive this. But escape velocity looks like the square root of 2gm over r. That's escape speed. And they want to know if we start with half that, then what height is it going to make it to? So that's going to look like this. I'm starting at the surface of the Earth, where I will have both universal gravitational potential, a whole radius of the Earth's worth, and also kinetic energy, half this worth, right? and then I'm going to make it up to I don't know how high, where I will only have this, right? And I don't know how much this will be, but I want to have it as some multiple of radii of the Earth. So I guess I could call it some multiple k times the radius of the Earth. Maybe k is a bad choice because of that k. I'll make it a small k. It's all right. All right, so at the beginning here, I have negative g mass of the Earth times mass of this thing divided by the radius of the Earth, right, plus 1/2 m v squared, and they said I have half the escape speed, so half of that would be this over 2, so I have that thing. I'm squaring this, remember, and then it was over 2, and I square that, that'll be a 4. Right, so that's escape speed over 2 squared. That's the v squared. And then when I get up to the tippy top here, I have negative g m over the radius of the Earth plus some other number of radii of the Earth. So that's not too pretty, but let's see what we can do with this. The g m cancels out in all of the terms. So canceling that out, I have negative 1 over RE plus 2 over 4, that leaves me a 1/2 times 1/2, so that's 1/4 R. If I cancel that out right, I think I did, equals, negative 1 over RE plus KRE. Okay, get a common denominator here. My common denominator, now that will look like negative 4R plus RE all over 4R times RE. Wait a minute, what's this R here? This is another R. Dang it. That's another RE, isn't it? Why did you tell me that? So that's going to make this a little easier, because now you could multiply this whole equation through by RE. Sorry, I just stuck another R there, but that's the radius of the Earth, isn't it? So multiply the whole equation through by RE, and then I get negative 1 plus 1/4 is equal to negative 1 over 1 plus K. And this fraction here is negative 3/4, which is negative 1 over 4/3. Why the heck would I write it like that? Because then, when I look at it like that, I can see that 1 plus K must be equal to 4/3, so K is equal to 1/3. There's more than one way to algebra your way to that. So if K is 1/3, then what did the question ask? Its initial speed. What multiple of Earth's radius gives the radial distance, the projectile? So the total radial distance would be 1 1/3 times the radius of the Earth. So the total radial distance would be equal to 1.33 times the radius of the Earth. All right, that's for A. For B, we got, what if its kinetic energy is half the kinetic energy required to escape Earth? So the kinetic energy required to escape Earth, since escape velocity Well, this is where I'm going to do the same thing I did in the problem that got all messed up there and see if it works this time. The kinetic energy to escape is equal to the, by the same argument before that, at escape, well, like when we've completely escaped, the total mechanical energy is 0, which means you have to have total mechanical energy of 0 at the surface. So that means the kinetic energy has to equal the opposite of the gravitational, right? This is the kinetic energy to escape. And it's exactly this relationship that we used in the notes to get the escape velocity, right? We did the, so kinetic energy of escape, 1/2 mv escape squared is equal to the opposite of this, that's gm m over r, and then the m's canceled, and we multiply it by 2, and that's where we got it, right? So I'm not crazy. So here, that means the kinetic energy required to escape is equal to gmm over r, right? And then if they want to only give us half that, then I have gmm over 2r, right? Which happens to be the same as kinetic energy for orbit, but that's not what we're doing here. So they want to know how high it's going to go if that's our initial kinetic energy. So if you remember what our equation looked like before, at the surface of the Earth I have both of these, and then when I get to my maximum height, and this time I'll do it a little differently, I'm just going to call that whole thing h. When I get to that whole maximum height, or I guess I should call that r, right? That radial distance, then I only have this. So my equation again looks like negative g m m over r. The r for this is just the radius of the Earth, plus the kinetic energy that it has here, and it told me that I have only half of what it takes to escape, so that's this, is equal to the universal gravitational potential when I'm all the way up there, which is negative g m m over my small r. And this one, sorry I did it again, that should be re, right? Because here, I'm here at that radius. Okay, so let's see what we can do with this. This and this combined together, we've seen this before. If I wanted a common denominator, I could just put 2's in there, so negative 2 of these means it's negative gmm over 2re is equal to negative gmm over r. So you can cancel stuff out, but you can also see those, since the numerators are equal, the denominators would have to be equal. So my radius, this is a full 2 radii of the Earth. And then part C, I don't know if we need to do any work here. It says, what is the least initial mechanical energy required to launch, required at launch if the projectile is to escape the Earth? Well, if you're going to make it all the way to escape, then here your total would have to equal how much you have at escape. And by definition at escape, at infinity, that's 0. And if I've just barely made it there, that means the kinetic energy is also 0. So this total mechanical energy has to equal this. It's 0. All right.